Welcome to the final video on Unit 8, Acids and Bases. Today, our focus is going to be on buffers, the Henderson-Hasselbalch equation, and buffer capacity. You'll find that buffers have a great use in chemistry, in particular in biochemistry, where buffers are materials that resist changes in pH. And we'll talk a little bit about how they work and how we can calculate the pH of chemicals that are in buffer solution. Let's take a look at our student learning objectives. First, you should be able to understand how and why buffers work and what they are used for. You should be able to evaluate the pH of a buffer by using the Henderson-Hasselbalch equation and determine how changes in the concentrations of materials in a buffer directly impact the capacity of the buffer to prevent changes in pH. Let's dive on in. First, let's talk a little bit about buffers. Buffer solutions contain large amounts of a conjugate acid-base pair. Something really important to think about is that this must be weak. You cannot have a strong acid-base buffer solution. In this instance, the conjugate acid reacts with the added base, and the conjugate base reacts with the added acid. So if I have a buffer solution and then add an acid to it or a base to it, it is going to stabilize the pH and prevent change. That is, it is going to either neutralize the acid or neutralize the base, preventing changes in pH. So if I look at the bottom here, which of these conjugate acid-base pairs will not function as a buffer? Well, the first one will, because it is a conjugate acid-base pair and it is weak. Same with the bottom one. It is a conjugate acid-base pair and it is also weak. But if I look at the middle one, HNO3 and NO3 minus, while they are a conjugate acid-base pair, it is a strong acid. And remember that strong acids cannot behave as buffers. So buffers work by having added acid react with the conjugate base or having added base react with the conjugate acid. So let's consider a solution of acetic acid in the acetate ion. If I were to add acid to this, so we add H3O plus into this, it is going to react with the conjugate base, thus resulting in our acid and H2O. So you notice that there is no H3O plus anymore. So if we add H3O plus, it neutralizes it. And if we add base, well, the base is going to react with the conjugate acid that we put in, thus eliminating the OH minus and preventing the pH from changing. Blood works as a buffer solution to keep the pH between 8.1 and 8.3. So you can see how very specific it is in terms of being able to maintain a proper pH. Just so you know, it uses the HCO3 minus and carbonate ion as its conjugate acid and base pair. Well, we can calculate the pH of a buffer by using the Henderson-Hasselbalch equation, which states that the pH is equal to the pKa plus the log of the concentration of the conjugate base divided by the concentration of the acid, where the base and acid are equilibrium concentrations of the conjugate acid-base pair. Recognize that by adding small amounts of acid or base does not really change the ratio. Thus, an insignificant change in pH occurs. The change in pH would be much greater if there were not a buffer because of the added hydronium ion or hydroxide ion concentration. So let's look at a practice problem here. What is the pH of a buffer that is 0.12 molar lactic acid and 0.10 molar in sodium lactate? Your Ka value is 1.4 times 10 to the negative fourth. Well, this can very easily be calculated using the Henderson-Hasselbalch equation. We do need to understand, though, that 0.10 molar in sodium lactate gives us our conjugate base because sodium lactate is soluble. So we're going to get the conjugate base when we put that into solution. And that will be 0.1 molar of our conjugate base. So as a result, we're just going to take the information and plug it into our Henderson-Hasselbalch equation. pH equals pKa plus the log of the base over the acid. I plug in my numbers. So pH, remember pKa is the negative log of the Ka value. It is 1.4 times 10 to the negative fourth. We're going to add the log of the concentration of the base, 0.10, divided by the concentration of the acid, 0.12. And what we end up with is pH of 3.77. So again, a pretty straightforward to go ahead, plug in, and solve. The last thing I want you to understand is buffer capacity, and that is the ability to resist changes in pH. The ability of the buffer to resist changes in pH is directly correlated to the concentration of the conjugate acid-base pair that you put into it. So the resistance changes in pH increases as the concentration of both buffer components is increased. Key thing there is both buffer components. Because when the buffer has more conjugate acid than base, it has a greater buffer capacity for added base because it will react with the conjugate acid to neutralize it. And then when the buffer has more conjugate base than acid, it has greater buffer capacity for added acid because there's more conjugate base to react with the acid than vice versa. So just kind of keep those things in the back of your mind as you think about buffer capacity and potential changes based on whether you have greater conjugate acid or greater conjugate base. Pretty straightforward video here, but hopefully you now can understand how and why buffers work and what they are used for, evaluate the pH of a buffer by using the Henderson-Hasselbalch equation, and determine how changes in concentrations of materials in a buffer impact the capacity of the buffer to prevent changes in pH. Again, appreciate your time with this acid-base unit. Next, we'll be moving on to applications of thermodynamics. Have a great day, guys. We will talk to you later. Bye-bye.